Hi everyone, it's Farnaz. I'm going to be going over the in-class workshop 1, conjugated molecules. The link online to the blank workshop was broken or something, so I couldn't pull it up, but hopefully you all have your copies in front of you, and let's start going over it. I think that before we start doing 1A, we should really go over 1C, because that just gives important concepts of like electron donating and electron withdrawing groups that you should be familiar with. So I'm just going to draw these out really quickly. Okay. Now, first of all, let's talk about what is an electron donating and what is an electron withdrawing group. Electron donating group, or you could call them EDG, donates electron density. And in what situations would this be beneficial? Would it be more beneficial if you have a positive charge, or would it be more beneficial if you have a negative charge? Well, think about it for a moment. And the answer is going to be when it has a positive charge. So imagine you have something that is positive. And what does that positive charge mean? That positive charge means that it doesn't have any electrons. So you would want something that would donate electron density in order to make it less positive, in order to bring it more towards the neutral side. But for instance, if you had a negative charge next to an electron donating group, that wouldn't be a very ideal situation, because right now you already have extra electrons, you already have the negative charge. So donating electron density, you're just going to be making that negative charge even more negative. So this isn't going to be a favorable situation, which we will see in later examples. And then you have your electron withdrawing group, or EWG, and this removes or withdraws electron density. And this is going to be literally the exact opposite of an electron donating group. So in which situation would you think an electron withdrawing group would be beneficial? Would it be beneficial with the positive charge, or would it be beneficial with the negative charge? Now the answer for this is of course going to be, it's going to be more beneficial if you have it next to something. If you have the negative charge, it would be more beneficial to have an electron withdrawing group next to it, because the electron withdrawing group is going to remove or withdraw some of that electron density in order to make that negative charge that you have a little less negative, more towards the neutral. So let's go up here and look at this. You have just a basic methyl group, and your methyl group is going to be an electron donating group, and it's going to do so through the theory of hyperconjugation. It's going to be a little bit lengthy to get into the whole explanation of that, but I don't think the explanation is really important. Now, what do you think B is? So I just drew in the electrons for B, and I'm going to give you two examples. Would it be better to have this, or would it be better to have this? So now notice what the oxygen has on it. The oxygen right now has on it electrons, right? It has lone pairs. And what do you know lone pairs to do? Lone pairs, when you want to draw a resonance structure, those are going to be something that you're going to be able to move. So I could draw a resonance structure. So now you just got rid of that positive charge that was previously on this carbon. Let's call that carbon 1C. So you got rid of that positive charge, and you delocalized or pushed that positive charge onto this oxygen. So now you have this positive charge delocalized amongst two atoms. You have it delocalized on the oxygen and on the carbon. So this is going to be a relatively relatively more favorable, because you're going to be donating some electron density to that positive charge. Now, in the situation that we have under it, this isn't going to be a very favorable condition, because you have something that's going to be an electron donating group right next to a carbon that has a negative charge. So what this is going to be doing, it's going to be donating electron density onto this negative charge, making it even more negative. And as we all know, you want to be as close to neutral as possible, so making it even more negative is going to be really bad. Okay, so this is also going to be an electron donating group. Now, what about the carbonyl? So we have your carbonyl, and I'm just going to draw the same two situations that we had above. Now, which situation is going to be better? Remember, this carbonyl, while it does have the lone pairs, it's not going to be able to donate those lone pairs down. This is not going to happen. Okay, so I know a common pitfall that a lot of students first being introduced to this concept have is believing that anything with lone pairs is going to be an electron donating or an electron withdrawing group. Or it's going to be an electron donating group, not an electron withdrawing group. But what you actually have to pay attention to is the flow of electrons, not necessarily the presence of the lone pairs. So this isn't going to be able to donate the electron density. It's actually going to be pulling up electron density. So basically what it's going to be doing, it's going to make this positive charge even more positive. So you could call this your electron withdrawing group. So now it's going to be beneficial in a situation where you have when you have the electron withdrawing group right next to a negative charge, because it's going to be able to, let's draw in like lone pairs over there, it's going to be able to pull those up, and you could draw out another resonance structure. And did you see what just happened? We just delocalized that negative charge between two atoms, as opposed to here where the positive charge is still there and it's not being delocalized. So we're going to say this is an electron withdrawing group. And you could follow the concept throughout with both D and E on your own. I just want to get into a situation that was not touched upon in this workshop. I'm pretty certain that the professor talked about it during class, but what happens when you have an ester? So this is our ester. Because as you recall above, we said that the carbonyl is an electron withdrawing group and the ether is an electron donating group. Technically, an ester is a combination of both the carbonyl as the electron withdrawing group and the ether as the electron donating group. So which one do you think you need to follow through? Well, this is something that's a little bit tricky, but once you understand it, you're going to be all right. So what you have to do is you have to see which part are you dealing with. So let's label this R1 and R2. Okay. So if you're in interaction, as you see, R1 is in direct proximity. It's in interaction with this carbonyl. And we know the carbonyl is the electron withdrawing group. So what's going to be happening is on this side, where the R1 is, the carbonyl is going to be withdrawing electron density. But as we see on this side with R2, that's in direct contact with the ether as an electron donating group, this ether is going to be donating electron density. So in what situations would it be beneficial to have like a positive charge or a negative charge with your ester? Okay, so as you see, we talked about electron donating group. An electron donating group, since it's donating electron density, it would be beneficial to have that next to a positive charge, or to have the positive charge next to the ether, because the ether portion is going to be donating the electron density. On the other hand, if you look at the other side of the molecule, since this is an electron withdrawing group, a negative charge is going to be happier next to that electron withdrawing group, because as you remember, it's going to be able to resonate up. So basically, the entire concept of electron donating and electron withdrawing group is how the electrons flow. As in other words, what's the resonance structure? So if I'm pretty confident that you all have great resonance structure drawing skills, so this shouldn't be that big of a hurdle to get by once you know that resonance is honestly the only thing that you're looking for. So again, in terms of the ester, the main thing that you're going to be looking at is you're going to have to determine which half of the ester am I dealing with. Am I indirect? Is my charge attached to this carbonyl, the electron withdrawing group, or is my charge attached to this, the electron donating group? Okay, so now that we touched upon the concepts, I think going through 1A and 1B is just going to be really fast. Okay. Okay, so now we're trying to compare 3 different carbocations, right? And excuse me. Now, what we talked about previously, when you have the positive charge, it's going to be most beneficial to have an electron donating group, because that electron donating group is going to be donating electron density into the system, and it's going to be making the positive charge that you have less positive. It's going to bring it more towards the neutral. So we're going to go through and we're going to identify if you have an electron donating group or an electron withdrawing group in your system. So right now I'm able to identify a methyl, and we know a methyl is an electron donating group. And I'm able to identify over here, we have our ether, and you know our ether is also an electron donating group. And then lastly, we see that we have a carbonyl, which is an electron withdrawing group. So automatically you should be saying that I have a positive charge. I have a carbocation right next to an electron withdrawing group. This electron withdrawing group is just going to be pulling even more electron density away from my positive charge, and it's going to make it even more positive, and this is going to be really, really bad. So we could automatically, right off the bat, say that this is least stable. So then comparing A and B is you're going to have to be looking at the strength of your electron donating group. So your methyl, as we talked before, is donating electrons through hyperconjugation. But it's donating electron density through hyperconjugation. But in B, you're also donating electrons, but you can see that these electrons actually are going to be donated in to that pi orbital system. You're going to be like sharing those electrons with it because you can draw your resonance structure. So B is going to be a more stable electron donating than the methyl. Okay, so this is going to be the most stable. Okay, so now we're going to get onto 1B. 1B is literally the same structures as 1A, but as opposed to the carbocation, you have the carboanion. So now, when you have the carboanion, what is going to be more beneficial? The more beneficial option is going to be that electron withdrawing group with your negative charge. Right? Because that electron withdrawing group, it's in the name, it withdraws electron density, it pulls away negative charge, and it leaves that area, it's going to make that negative charge a little less negative. It's going to bring it towards neutral. So again, we're going to go through and label what groups we have. We have an electron donating group, we have an electron donating group, and we have an electron withdrawing group. Woohoo! Electron withdrawing group withdraws negative charge. And you can see to draw that resonance structure, and it just withdrew all of that negative charge, so this is going to be the best option. And then what about between A and B, because you have electron donating groups in both. So then again, this goes into the strength. So which one is the stronger electron donating group? Just like how in the previous question, when you're dealing with your carbocation, the most stable one was B, because B had the ether as opposed to the methyl, and the ether was it was a stronger electron donating group. So this is strong. Whoops. And this is weak. So the stronger electron donating group is going to be even better at donating negative charge. So it's going to make this even more negative than the weak electron donating group would. So this over here is going to be the worst. Okay. Now let's go on to 2. Okay, now this is actually going to be showing us an important concept that I didn't really mention previously. Even though you have electron donating group in association with your positive charge, and what I mean with in association, I mean literally on the same compound, it doesn't always work, as in that electron donating group isn't always going to have an effect on that positive charge, in the same way as an electron withdrawing group isn't always going to have an effect on the negative charge. It all has to do with, is it directly related to it? So this comes into play of drawing your resonance structures. So this electron donating group, let's pretend it has a lone pair, is going to be donating electrons here, which will go here, pushes this, pushes that, and it's donating electron density into this positive charge. So I would say this is a pretty good electron donating group. Now what about this one? It has a lone pair, it's donating here, but it's going to be pushing these electrons over. It's not going to be affecting this positive charge whatsoever, because it's not really in conjugation with that positive charge. So I would say this, while it's not great, because your electron donating group isn't donating any electron density to where you want it to go. It's actually going in the opposite direction. So we're just going to run through the line with this, and we're going to follow through with the same idea. So this is going to be a good electron donating group because it's going to be donating electrons into the area where you need it, where you have that positive charge. Now, you want the electron density to go this way, but you can't make this happen. That bottom arrow will not happen. You have to go with the flow of the electrons. It would go down and be pushed in the other way. So it's not really bothering with this positive charge. It's not helping that positive charge be less positive. So this is bad. And then electron donating. And I forgot to draw the positive charge over here. So it is donating electrons, as you can see. It's donating electrons, and I have made a mistake. Okay, let me just redraw this molecule a little bit. Woo! Let me redraw this molecule a little bit bigger, and I'll show you the mistake that I have made. So let's say we have lone pairs over here. And this carbon has another hydrogen. This lone pair is going to donate in. There's not going to be any driving force to push these electrons over. So it's actually, if I want to draw the resonance structure of it, the resonance is going to be this. Because the reason why, in this example, we pushed the electrons over was because we didn't want to break the octet rule. Because you have a hydrogen over here along with the double bond. When you bring these electrons down, you're going to have too many bonds here, so you're going to have to push these electrons over, and that's the chain reaction that's going to happen. The chain reaction isn't going to happen in this one, but it does still have an effect to that positive charge. It is delocalizing that positive charge, so I would say this is a good compound. Okay, everybody, that's going to be all for workshop 1. The next questions is just straight up synthesis. Practice that on your own, and if you want, post it onto the Facebook group, and I'm sure one of your fellow students or even a undergrad TA would love to check over your synthesis. But for now, that is all. Good luck with your study.